everyone, and welcome back to Behind the Scrubs. I'm your host, Marianne. As a part of our 3-episode series, I have been on a mission to show the insights of the radiologic technologist role. For those of you who are new to the podcast, the last 2 episodes explored the who and what of a technologist. This being the final episode, we'll discuss the importance of equipment testing and how it impacts patient safety. Today, I am joined by Jonathan Zinyu. He is a registered radiologic technologist based out of North Carolina. Please tell us a little bit about yourself.
Hi everyone, my name is Jonathan. I've been working within the radiology field for about a year now, and so far, it has been a very fulfilling experience. When I have off time, I love to travel and spend time with family. I have a dog named Elvis. He's the most handsome, handsome guy in the whole wide world.
Aw, all right. Well, Jonathan, I've got a few questions for you today. How about we get started?
Let's do it.
All right. In the context of medical imaging, tell me a bit about what quality control is. How does your role as a radiologic technologist contribute to maintaining the process?
Quality control is part of overall quality assurance. It is how quality standards for imaging equipment is confirmed and upheld. As a radiologic technologist, we are responsible for performing a series of tests every 6 months to certify a satisfactory operation and functionality. Our testing ensures that image production remains high quality and without repeat patient exposure.
When it comes to quality control testing, how do you know what regulations you have to comply with?
Well, the FDA's Center for Device and Radiologic Health is who enforces public health protection through assurance of patient-provider access to safe, effective, and high-quality medical devices. Safe radiation-emitting products are their primary mission.
Let's say that it is the day for your semi-annual QC testing. What does your routine check of the radiographic equipment look like?
When we monitor equipment performance, there are typically 3 objectives to follow. We monitor image processing system quality, we measure external beam quality, and we identify faults within these systems to allow any corrective measures to be taken.
Yep. So research shows that a working quality control system lowers the number of repeat exposures and therefore reduces the dose to the patients. You would have some really satisfied patients, am I right?
Well, granted, there are many other factors that go along with it, but yes, dose can be reduced to our patients.
The purpose of QC testing medical imaging equipment seems to follow assurance of proper functioning and production of quality images for diagnosis. I'm sure our audience would applaud technologists such as yourself for always maintaining patient safety. If a malfunction were to be suspected, what are some clear indicators that a technologist would recognize? What does the reporting process look like?
Typically with malfunctions, you will see things such as image artifacts, inconsistent output, mechanical issues, or even system error messages. Output may present itself as grainy images, which could be caused by general detector concerns. Inconsistent display of image contrast and elevated radiation levels are not uncommon occurrences from malfunctioning equipment. Now, when it comes to handling these situations, it is important to stop equipment operations. The supervising manager or the facility radiation safety officer should be also notified.
Over the past 2 episodes, I have come to learn that medical imaging companies are no longer supporting computing radiographic technologies. All things digital have become the new standard. With the periodic evaluation of detector systems, most DR vendors now offer quality control test tools. Could you elaborate a bit on digital detector calibration?
Firstly, you are correct with your impression of CR and DR technology used today. Field experts are continuing to develop new technologies even as we speak. Digital detector quality is primarily tested using a concept known as detective quantum efficiency, or DQE. The main objective of DQE is to lower the total radiation exposure required to acquire the highest image quality. Detector quality is represented by a value range of 0 to 1, where 1 depicts a perfect system. The closer the value is to 1, the higher the spatial resolution and overall image quality.
How is a technologist able to determine when system performance is abnormal? At what point would you inquire about system maintenance?
As stated previously, radiologic technologists are responsible for performing routine system testing. Periodic system adjustments are performed by vendor service personnel, but how often tends to be vendor specific? Let's say that during the QC testing process, a region of detector pixels appear over or under saturated compared to what is normal. A system equipment work order will be submitted. At least once a year, a medical physicist will perform a full inspection to ensure equipment meets the performance standards.
A little while ago, you acknowledged that computed radiography is no longer supported by many companies. Yet, the technology is not completely done away with. What does quality control testing look like in regards to CR-specific imaging receptors?
When used regularly, CR imaging plates should be erased daily, otherwise scatters captured in an unwanted image artifact will appear. Plates are flooded with an extremely bright light and ready for use once again. If this process is not completed prior to each exam, the possibility of double exposure becomes dangerous. In computer radiography, ghosting refers to an artifact which remains of a previous exposure remain on the imaging plate. A faint image will appear superimposed upon the current one due to the incomplete erasure.
So the plates are susceptible to double exposure. How about physical damage? Are these devices made to be durable, or do they become highly sensitive once they experience one instance of mishandling?
We technologists want to make sure our CR plates are always in tip-top shape. Semi-annually, these are visually inspected for cracks as well as surface markings. If any plates or create artifacts, they are removed for immediate use. These plates go through a lot each day, and it's our responsibility that we take care of them.
Oh wow, I was not aware of how sensitive imaging receptors are. For image resolution, how would a technologist ensure that it reaches quality standards?
Focus box size plays a very important role in image sharpness. For appropriate spatial resolution, focus box size should be kept within 50% of the size stated in equipment specifications. Spatial resolution considers how sharp the image quality really is. To assess this, there are a multitude of unique tools we can utilize. The most common tool is conducted with the line pair resolution tool. This tool encourages demonstration of the smallest line pairs to be seen within a test image. The lines visualized are compared to those on the tool, and the line pairs per millimeter are determined given resolution. Being able to see very fine lines allow us to say that high spatial resolution is achieved, and therefore a high quality image.
Just as detector maintenance is crucial, the assurance of quality display monitor resolution is also essential to the production of high-quality images. For radiographic interpretation, radiologists often utilize top-of-the-line monitors that read medical images with clarity and efficiency. Modern screens are designed to reduce eye strain and improve diagnostic accuracy. What sort of testing ensures resolution and brightness remain great at all times?
The resolution is visually inspected by using a tool called the Cinti test pattern alongside a standardized grayscale tool. Perhaps you may be familiar with the Cinti tool as color bars displayed on your home TV. A few decades ago, this tool was often used to calibrate color for tape records.
Now that you mention it, I do.
Hooray!
Okay. Well, being able to represent a full range of grayscale levels is essential to image interpretation by the reading radiologist. Rendering levels ensure consistent contrast perception across the entire display, no matter the luminance range.
So bringing light to the situation, many in the radiology field seem to work in the dark. How important is monitor luminance? Is brightness vital in determining image quality or clarity?
Not only is adequate contrast important, but assurance of optimal display monitor brightness is too. Both work together to contribute to image interpretation. We can test brightness through inspection of brightness uniformity. Comparison of brightness across the central monitor to its corner edges must produce a value within 15% of the other.
Really quick, let me tell you a story. I recently went to get my semi-annual teeth cleaning, and this trip required yearly x-rays. The dental hygienist provided me with quite a heavy apron for radiation protection. However, when I broke my little toe not too long ago, I had to get another x-ray. During this exam, there was no apron to be found. I did not question this, but now that I have the opportunity, how about you answer my question? What is the purpose of the apron?
I'm glad that you asked. Let me tell you about the magical world of shielding. Lead shielding minimizes exposure risk to radiosensitive body parts such as the thyroid and gonadal regions. Shields help ensure radiation safety standards are being followed according to the LAR principle, or as low as reasonably achievable when pertaining to exposure.
So, like your equipment, do lead shields have specific testing regulations?
Over time, depending on use and age, lead aprons can develop internal defects such as cracks. Defects like this often compromise the user's exposure to unnecessary harmful scatter.
I am aware that technologists make use of their hands regularly when positioning or holding patients. Are there any protective measures for this part of the body?
Why, yes, we call them like gloves. These protective gloves can be used to reduce the amount of scatter radiation that reaches workers' hands during an exam. The gloves are lead-lined, and QC testing follows the same regulations as our lead aprons. Both protective shields are routinely exposed to X-rays during test exams. The purpose is to detect any cracks or other defects within the lead. If any are found, shields will need to be replaced because they are no longer providing adequate protection. As you know, nobody wants to be blasted with unnecessary ionizing radiation. Am I right?
Anyway, to ensure that no unnecessary radiation reaches the patient, what kind of beam restriction testing is done? How do you ensure that functionality remains consistent to reduce patient exposure and image repeats?
When it comes to collimator and Bucky tray alignment, we must limit the possibility of inaccuracy. The physical light field to radiation field accuracy is considered very important. We are only allowed a 2% variation of SID when tested. A very unique test, known as the 8 or 9 penny test, is often used to verify this. At first, the technologist will collimate the light field to a predetermined field size. 4 pennies are placed just within the borders of the field, and another 4 pennies are placed outside the field while touching the inner pennies. Then an exposure is made. Though inspection of whether any pennies were cut off or not, we can determine if any misalignment falls within or outside of the 2% deviation.
How cool! It would be quite interesting to witness this test in action. Now, correct me if I am wrong, but it seems that much of the radiology field is closely tied to perfection. When you make an exposure, would you say the sense of perfection is instilled or goes away?
When it comes to this field, radiology workers must strive to be as precise as possible. We are held to a very high standard in terms of accuracy and image quality. The ultimate standard for exposure centering should be within 1% of the light field central ray. As a technologist, I choose to strive for perfection, although I know that is not always possible.
All right. Well, that is all we have time for this week. Thank you, Jonathan, for joining me on the podcast.
It was a pleasure. Thank you for having me.
Don't forget to tune in to Behind the Scrubs next week for a sneak peek trailer on what is to come. Bye, everyone.